Well, welcome to the last day of new content in IPM. Congrats on getting almost all the way through the spring semester. I know there's still that final push to get through, but we are getting pretty close to that final half week. That's pretty exciting for everybody. So today what we're going to be focusing on is looking at an actual case study of IPM that was kind of built from a place of zero management recommendations all the way up to a full-fledged program that's very much in swing right now. That's focusing around low desert cotton IPM in the American Southwest and northern Mexico. But before we hop into that, announcements as usual. Again, the Thursday monitoring lab reports will be due today. I've already had a handful of you stop by the office. I'm sure you're all aware. So turn it in at least by the end of the lab time today. And we will be having lab at Bayer Crop Science. This is going to be the last one. We're going to go out, we're going to count our LEPs, and we're going to run through some basic data analysis before we dismiss. One note, and I put this on Blackboard, I mentioned this in past lectures, but again, there is no van today. There's some big FFA events. All the vans are solidly booked, and been booked for like a month and a half. I've been checking in about every week, and they're not budging. So looks like you're going to have to find your own way. If you absolutely can't find a ride, talk to me after class. We can try. Sorry? Yeah, Uber out to Bayer Crop Science. Wouldn't that be fun? All right, so we just have 2 more lectures left. We have today's lecture. And then we've got the next Tuesday, which is going to be a review session again, covering sort of the first 2/3 of the class primarily. Then we have the final exam, which, as I mentioned before, is semi-cumulative, mostly focused on stuff that we've covered recently, with a little bit of stuff covering broad topics from the rest of the course. So like I mentioned a second ago, I think a useful way to kind of wrap up IPM and to try and get an idea of all of the major topics we've covered is to look at a program where IPM has been established recently and just seen all the work that goes into creating sort of a self-sustaining management plan that is sustainable moving into the future. And a really nice example of this is the growth of lowland cotton in the low desert farming. So low desert basically just means any desert that is less than 2,000 feet in elevation. If you're in, say, parts of like the Mojave Desert, that's high elevation desert. And they have very distinctive sort of agricultural practices. So for the sake of this IPM example, we're talking about primarily agriculture in the Sonoran Desert. And this includes a variety of areas that have slightly different cropping practices. And this is all based back in the mid-1990s. So when I talk about the things that are being grown in these various regions, I'm talking about the agricultural practices in the 1990s. Things have shifted a little bit. Cotton has become less prevalent, but this is all based in the system at the time. So primarily, these are areas including the Imperial Valley in California, which at the time was growing melons, veggies, a little bit of cotton, but was really dominated by alfalfa. Central and Southwest Arizona, which are generally cotton-heavy, but with a fair number of lettuce and melon growth going on in Southwest Arizona. And then 2 valleys in Mexico. We had the Mexicali, which is right here. This is a valley that is a huge cotton production area in Mexico, with a variety of other crops planted in there, sort of at lower levels. And then finally, the Yaqui Valley, which was sort of down here along the Gulf of California, which is primarily winter wheat and a sort of smattering of summer crops that were thrown in there, including some melons and odds and ends like that. And so the pest that really kicked into overdrive the need for an IPM system was this guy, Bemisia tabaci, or the Silverleaf Whitefly. This is a common pest that you should be familiar with. We talked about this on and off throughout the economic entomology course, but this is a common pest across a wide variety of crops, and it has a lot of the features that make for difficult pest control. It's highly polyphagic, meaning it feeds on lots of different plants. It has 200 different plant hosts. Amongst those 200 hosts, about 60 of them are crops, which it causes economic damage to. So there's a wide variety of crops it feeds on, but it is especially problematic in vegetables. So lots of times in lettuces, cucurbits, some cole crops, and but also cotton. It can be very problematic in. The other area you see a lot of whitefly problems would be in greenhouses, on ornamentals. That's a common place you get lots of whiteflies. So these guys are very small. They are, anywhere from about 1.5 millimeters to 0.5 millimeter long, depending on the life stage. And they have these nice mobile adults that look just like little tiny white flies. And then the larvae are this sort of sessile, clear form. They almost look like little egg sacs or shed skins. They can be a little bit hard to spot on the leaves. And so the major problem you have with these guys is sort of the typical stuff you see with hemipterans, which they are, which is that they're going to be feeding on photosynthate, and because these guys can grow populations very quickly, they can cause a lot of direct damage, stunting growth, causing leaf drop, yield losses, and also, when they feed, they produce lots of honeydew. So you see lots of sooty mold growth. In cotton, if you have large populations, the honeydew will stick to the cotton bolls and give you what's called sticky lint. And sticky lint is much harder to gin, harder to process in general, and it fetches a much lower price than clean lint. And then indirectly, you have to deal with a lot of disease and sooty mold growth as well. Now, Silverleaf Whitefly had been an existing pest in the system for a long time. It had been established in sort of the Sonoran Desert since the 1920s, but for whatever reason, it was just never a big pest problem. The particular genetic variety that they had, what they call the biotype, wasn't really well suited to the crops they had, and so it would be an occasional pest. You would go out and spray it with a pyrethroid, and it would die down, and you would be fine. So it wasn't a really big problem. But in the 1980s, a new biotype showed up, so a different genetic variety of the whitefly. These guys were called biotype B. And biotype B turned out to be much more well-suited to the crops grown in the area. They were really excellent at feeding on melons and cotton in particular. And so very quickly, they started displacing the other biotypes that they had and really establishing themselves and causing a lot of damage. And as I mentioned earlier, a lot of the damage we were seeing was very serious. This is an example of a cotton boll with a sticky lint going on. So it has enough honeydew on this one in particular that you actually have sooty mold growing on the lint, which makes it really hard to market. By the 1990s, infestations were significant enough that more or less in the Imperial Valley, Southwest Arizona, and Mexicali, so sort of that triangle right at the Arizona-California border, they were seeing significant losses in vegetables, melon, and cotton. And by 1992, it was the most devastating pest in the entire system, all the way down to the Yaqui, up to the Imperial and Central Arizona. To the extent that more or less melons that were planted in the summertime at peak whitefly season were completely lost. There was virtually no harvest, 50% loss in cotton in certain regions, and cotton that was harvested was bumped down to a lower lint quality level. And so what they did harvest, they got a much lower price for. And the thing is, I'm not sure if this is still the case, but at the time, cotton prices weren't determined individually between farms, but cotton was determined on a regional scale based on ginning. And so if you had a majority of farmers who were having sticky lint problems, it pushed down the price for everybody, even those who had high quality cotton. And so it was a sort of devastating effect economically across the entire region. And so this really kicked people into this desire to create a management plan. And the problem was that essentially they had no management plan in place at all, because this had been a very rare, occasional pest that didn't cause a lot of problems. So more or less, all of the researchers, all of the growers, all the extension agents were starting at square zero. And so they did some of the basic stuff that they thought they could do right off the bat. They shortened the cotton season. So essentially they planted earlier so that they could reduce the amount of exposure the cotton had to the whitefly. They started synergizing pyrethroids to make them more effective against the whitefly. And by that I mean basically they mixed pyrethroids with organophosphates. So they mixed two different modes of actions together. And this worked for a while. It did control the pest, so they could actually get harvest. They could harvest melons. They could have relatively high-quality lint. But the problem was it was crazy expensive. 1993, at the time, was the greatest amount of money ever spent in the Sonoran Desert on pest control. And so they were really cutting into any sort of profit they were making. And then, as that just seemed to be working, B. tabaci developed resistance to these synergized pyrethroids. So all of a sudden, they lost their only tool that was really effective. And so 1993 had been previously the most expensive. 1995 was off the charts. So, actually, never mind. 1994 was the highest. So what we have here is the actual costs of the insecticides. And we can see that it's sort of level here around the time that whitefly outbreaks are really terrible. Whitefly on this, so this chart is basically cost by year, and then in each individual column you have sprays dedicated to individual pests. So you have whitefly in the lightest color at the bottom, pink bollworm in the middle, lygus bug here at the next to the top, and the very top one is all other pests. So you can see whitefly is kind of a minor component until the huge outbreaks in 1992, where it's the majority, 93, 94, and then in 95 we just have a huge outbreak year. Tons of sprays going on and tons of resistance in the system. But then, in 1996, we saw a reduction in these whiteflies, and productivity was largely restored. And more or less after that 1996 point, it's been under control ever since then. Occasional outbreak years, but nothing near what they saw in the early 90s. So, what happened at that point? What happened in 1996 that kind of shifted things around? Well, primarily what happened in 96 was we saw the establishment, essentially sort of the fruition of all the research that was going on in the early 90s, looking at this pest, into a fully realized IPM system. So that essentially before they kind of had all these emergency measures in place, and in 1996, all of them came together to form a cohesive whole. And this is kind of a nice IPM system because they have a nice visual for it that kind of pulls everything together. And it's a system that has three major components. They've recognized the importance of having an effective sampling strategy, having effective chemical usage, and then finally having a variety of what they call avoidance techniques. So essentially we need effective chemical tools and some sort of strategy to use them in the most judicious way, and then we need a variety of cultural and biological techniques that will suppress the pest overall. So what we're going to do here is we're just going to kind of step through these individual stages, starting off at the top and moving down through avoidance. So what you'll notice on here is that within each of these sections, sampling, chemical use, and avoidance, we have little subsections. These are individual parts of the IPM program that have been fit together to work as a part of the collective. And so we'll be touching on those as well. Within these, just a little thing, WF would mean whitefly. And beyond that, it's mostly self-explanatory. All right. So starting out with sampling. So prior to biotype B showing up, there was virtually no need to sample for whitefly. It was an occasional pest. It didn't do really well on the crops. And so for the most part, people weren't really looking at it. And they didn't need a reason to go out and look at it. It was just kind of there. Every once in a while you'd come out and there seemed to be a lot of them, so you'd spray something. But once biotype B showed up, it turns out that not having a sampling plan is a surprisingly large problem, and it makes it really hard to coordinate growers and to implement any sort of plan for control. Because without that information, it's not really clear where the biotypes, where the whiteflies are going to show up on the plant. So where would you even look for them? Where is the most important place to check? And it makes it difficult for growers to communicate with each other to try and compare severities. If we're talking average number per leaf, average number per plant, average numbers for sampled over a certain, say, range, a square meter or something, it just becomes difficult for us all to talk on the same level about what our infestations are. And ultimately, without these guidelines for sampling, what generally happened was people just failed to monitor in any sort of significant way. There was a little bit of sampling, but you'd go out and look. If it seemed like there were a lot of whiteflies, you'd apply some sort of spray, which, as we know from our action threshold talks, is not the most efficient way to use our chemicals and is probably the sort of control applications that cause them to develop resistance to those pyrethroids. So one of the very first things that researchers wanted to do was they wanted to establish a highly reliable sampling plan. They wanted to come up with something that was simple so that growers or scouts could go out, take a look at a field in a very short amount of time, and come up with a highly reliable measure of whitefly populations that could be shared across fields. And so what they ultimately came up with was this idea that whiteflies tend to be blown around a lot by the wind. If there's any sort of rain event, they tend to get washed off. And so measuring up near the top of the plant is most likely to give you really unreliable readings. Because if you get a whole bunch of wind, it's going to knock the plants over, sweep all them off. So you want to sample down near the base of the plant. They said at the fifth leaf down from the terminal, or the top openmost leaf. And they reasoned that you needed to do two different types of sampling. First, you needed to check the leaf for adults. Main reason for this, well, I got ahead of myself. You want to check one for adults, and then two, you want a separate way to check for nymphs. And the main reason for this is that we have different technologies to handle different life stages. For the adults, we're talking about things like synergized pyrethroids that are adulticidal, whereas with nymphs, we're using things more like larvicidal growth regulators, or insect growth regulators that target immature life stages. And these two chemicals behave very differently from one another. Plus, the different life stages are telling us of different danger levels. Having a large number of adults can be something that needs to be treated very quickly, because if they have time to feed, mate, and lay eggs, you have a very large population coming down the road. Whereas with larvae and nymphs and the like, you're looking at potential future growth. And so that's more or less trying to get ahead of the problem that's coming down the pike. And so ultimately what they came up with was this scheme where you collect the fifth leaf down from the terminal, you turn it over, you count the number of adults that are on it, and then you would take a quarter, or something approximately quarter size, you would put it in sort of the crook of the two main stems of the, the two main veins of the leaf, and you would look at the area underneath it and see how many large larvae there were. And large larvae were basically anything you could see with the naked eye. So it was very simple, something you could easily do. And at the same time, they also created a sampling protocol to measure these guys in melon, because melon was a huge alternative host for these whiteflies. So, sampling is great and all. Now we can all sort of talk about the same thing. It's easy for growers to talk to extension agents, to talk amongst one another, and get an idea of how bad an infestation they have. But sampling really is of limited utility if it doesn't inform you on what you should do next. What is a big population? What is a small population? What will cause economic damage? And so the next big step that they had was to move out of that sampling and move down into this effective control or effective chemical use part of the pyramid, right here in the middle. And within this, we have setting action thresholds, having effective and selective chemistries, and managing resistance. So within the action thresholds,
why is there different action thresholds for application? I understand there's different applications, but I don't understand why the action thresholds are different.
For the two different chemicals?
Yeah, well, you have growers spraying 2 to 3 adults per leaf for ground application.
Oh yeah, I'm going to get to that in just a second. So the big thing that people wanted to ask the question of was, where do we even start in terms of these thresholds? What would be a good starting place, just to narrow down our experimental range? And so they hit the literature, they looked around, and they saw that people had done experiments establishing thresholds in various climates, Israel, Thailand, Singapore, and they had kind of had this consensus that treatment thresholds were somewhere between 2 adults per leaf and 10 adults per leaf. So that gave researchers an idea of where to start. Now, at the time, growers had kind of come up with their own threshold. They had gone to the more conservative side. They said, let's play it safe. Let's go for 2 to 3 adults per leaf, and we'll spray an application. But as was just pointed out by Dan, that they actually had 2 different treatment thresholds depending on how they applied. That's not the right aerial. Either way. And this was basically due to the perceived effectiveness of these two application techniques. There was this general perception that if you applied from an airplane, that the coverage wasn't as good, that your chemicals weren't as effective as if you sprayed using some sort of ground-based equipment. And so growers who were using aerial applications tended to use much more conservative estimates because they wanted to sort of nip the whitefly problem in the bud. And so essentially, if you're looking at these aerial applications, you're more or less treating if you have 1 insect per plant, well, per leaf. And so that's a relatively low rate of infestation compared to this 2 to 10. Excuse me. And also, there was a big question of what are our available chemistries? Because ultimately, your choice of when to treat is also going to depend on how effective your chemicals are, and whether you're going to have large amounts of control or very little control. And so at the time, they had 3 major options. In cotton, really just 2. You had insect growth regulators, which could control nymphs, and were relatively selective. Primarily killed whiteflies, didn't really hurt your biocontrol. You had conventional insecticides, which were broad spectrum, but were really good at killing adults, so nice for adulticidal treatments. And then in melon, they had a fancy new chemistry that had just come out called imidacloprid of various fame and infamy now for the honeybee debate. But it was a nice systemic. It was very effective at killing all life stages. And finally, they wanted to determine, before they set this threshold, what is the goal of this control? What are we trying to protect here in cotton? Are we trying to protect a certain amount of yield? Are we trying to avoid a certain amount of boll drop? And ultimately, what they came down to was cotton stickiness, getting all that honeydew on the lint, is the most damaging aspect of these guys. It can depress the price of cotton across the whole region. So if we can set up a threshold that significantly reduces cotton stickiness, then we're doing our job, because we're basically elevating the output for the whole region, not just for some individual growers. And so essentially they created a whole bunch of field plots where they would infest at known rates, and they would measure the amount of damage, and they came out with 2 different thresholds. One for adults, that would determine when you would spray a conventional insecticide, and one for nymphs, which would determine when you sprayed insect growth regulators. And as you can see, they're relatively different from one another. We're talking about 5 adults on average per leaf, as compared to 1 large nymph on the area under the disc. But keep in mind that you're looking at the area underneath something the size of a quarter. So you're looking at a whole lot less leaf than you are when you're scanning for the adults. Plus, by the time you see a large nymph, that means that it's in a late instar, it's about to become an adult, and so you can estimate that there are many smaller early instar nymphs on the leaf that will become a problem later. And then what they did, and this was really nice, they actually simplified the whole process. So instead of having people go out and actually physically count the number of individuals on the leaves, they created a presence-absence test, where ultimately all you had to do was go out to a field, sample 30 of those 5th leaves down from the terminal, and you had to check, did they have adults on it, and did you have large nymphs under that quarter-sized piece? And then you would just check it as if they were infested or not. So what they did, which is kind of cool, basically researchers went out to those plots that they had infested at a known rate, and they counted the number of individuals on the leaf, and then they went through and they counted the total number of individuals on the whole plant. And they found that you could very tightly correlate the number of infested leaves in a field with the total whitefly population. Very, very tightly. So you didn't actually have to count, just had to know how many infested plants there were. So they ultimately came up with this thing that if 17 out of 30 plants had whitefly adults on that leaf, then you should go out and spray, because that is the equivalent of the 5 adult threshold. Similarly, if you had 12 leaves out of 30 that had large nymphs, or 40% infestation, that was the equivalent of your nymph threshold. And the big advantage of this was that it took the cost of sampling and pushed it down all the way to about $2.35 per acre. And the training rate for this ended up being something like, you could train people in about 30 minutes to do it, and on average, they timed out that a scouting of a total field took about 7 minutes. So it really accelerated the whole process, made things really easy for people to use. And as we've talked about before, one of the biggest things about getting people to use IPM is to make it so easy to use. And the nice thing was they compared this presence-absence test to actually counting, and they found that almost 97% of the time it made the correct assessment. It basically agreed with what the counts would be. There were 3% of cases where it gave false positives, so that meant it told the grower they needed to go out and spray when they really didn't need to. And then just 0.4% of the time you had a false negative, which is a case where it told you to not spray when you actually had an economic threshold. And so really, 99.6% of the time, you're really erring on the side of safety and correctness. So this was just a really excellent threshold, well designed. All right. So moving on to the next triangle, moving on from action thresholds to effective and selective chemistries. I touched on this a little bit, but the reality is one of the big things that was sort of inhibiting effective control of this pest was the fact that there were virtually no chemical tools that could be used against it when it first showed up. There were these synergized pyrethroids, but that was the only tool they had. And so by just applying it so frequently, they got resistance within about 4 years. So it wasn't useful. So one of the big boons that the IPM program had was that a variety of highly effective chemistries all came out right around 1996. So amongst these were imidacloprid, which was a neonicotinoid that was approved for melon and proved to be highly effective against all life stages. And then there were also 2 IGRs. There was, good lord, I don't remember the names, because they were like phenoxyprexin and bufuroni, who knows. Either way, Applaud and Pivot were the market names for these guys. And they were really ideal for really 2 major reasons. The IGRs were very selective, and so they provided nice control of the nymphs without killing all the biocontrol agents, but also all of these new chemistries, unlike the organophosphates and pyrethroids, were systemic, which is ideal against hemipteran pests, because you get that stuff floating around in the phloem, and you get nice targeted control that they can't avoid, because they have to eat. And so the IGRs were actually sort of pushed through the EPA a little bit faster than they were supposed to in order to get approval for cotton. And the EPA basically said, you can apply these on cotton, but we're going to put a rule on this, which is that you have to put it in a very strict rotation regime. We don't want to see resistance against this. So they mandated that these 2 IGRs could only be applied 1 time per growing season. So that's kind of their rule right off the bat. And it was probably with good reason that they mandated that, because whitefly is one of the fastest evolving insects that we deal with. It's got resistance to more than 40 insecticidal active ingredients across a wide variety of modes of action. And as such, it was expected that resistance would come down the pipeline quickly. And so growers really lined up on this, because they were real excited about these new technologies. And they came up with a resistance plan that had 3 major steps, which was that First off, pesticides could not be applied until that action threshold was hit. So they were going to cut out any sort of preventative sprays. You only took care of the problem when it showed up. So reduce the total amount out there. They were going to follow the EPA mandate, which was that you could only apply the IGRs once per season. And then finally, they were going to follow a prescribed rotation scheme, where you move from your most selective products down to your most broad spectrums. So they started out with your IGR spray at the beginning of the season when you had your first outbreak. Then you moved to a non-pyrethroid targeted approach. And then finally, you would use your pyrethroid synergized mix as sort of a last resort at the end of the season if you needed it. Consequently, this developed into a very nice sort of scheme. This is something I downloaded from the, this is the cotton growing recommendations for the IPM plan that they published this in 2006. So this is something that has really stuck around. And whereas before it had, basically 2 chemicals in the first, 1 or 2 in the second, and 1 in the third, we've really expanded on chemicals in the first 2 stages. So there's now kind of a wide variety of things to feed on in the rotation. Excuse me. All right, and then finally, we have the last step, which is avoidance. And avoidance, moving from top to bottom, is the last step. But really, avoidance is the base of the pyramid, not because it's last, but because it is the base that all of the rest of pest control is put upon. Essentially, avoidance incorporates all practices that are designed to limit pest populations before they hit economic levels. So essentially, it's all of our cultural, all of our biological, all of our preventative control in one chunk. And the idea here is that the broader our base is, the more avoidance techniques we have, the more control we're going to have, and the less dependent we will be on chemicals. And so as far as avoidance is concerned, there's a lot to tackle in here. So I'm going to subdivide it into the 3 major sections, which would be crop management, exploitation of pest biology and ecology, and area-wide impacts. So crop management. Crop management really falls under cultural control, and this is essentially any sort of management that we use to make it harder for whitefly to establish in the field. So how can we manage our field to make it unfriendly to the whiteflies? And they found there were a variety of things they could do. One of the big ones was managing their irrigation systems. So at the time, irrigation for cotton was really based on flood irrigation, right? So you dump a whole bunch of water, you saturate the soil, you let it dry out over time, and then you go and apply another flood. Now the challenge with this was that with that long, prolonged drying period, the cotton was getting really stressed out. And hemipterans really like stressed plants. They do well on stressed plant systems. And so you were creating sort of an ideal host, something that the whiteflies could establish on very well. And so they moved away from using these flood irrigation systems to using drip or sprinkler head approaches, where you could apply the water more regularly, and as such have healthier plants overall. In addition to that, the sprinklers also had a nice effect, which is that they mimicked rainfall. And whiteflies don't hang on to plants very well in the rain, so by applying rain, it'll sort of cause them to scatter away from the crop, they'll fall off, they'll get washed into the dirt, where they're prone to predation or infection by a pathogen. So it's kind of a nice approach. And then the last thing was they had to deal with the irrigation in these melon crops. So at the time, there was this practice where what you could do is at the end of the season, you could just at the end of the season, when your melons are mature and ready to go, you could just sort of keep feeding them water. And that way the melons would stay on the vine, they'd stay healthy, and you could just keep waiting until the market got just right to sell your melons, sort of looking for a better price. But the problem with this was basically you were leaving out this ideal habitat for whiteflies to live in. So they would build up these big populations on all of these melons that could be harvested and then move off into other crops. And so they ultimately switched to a system where they got rid of all that late season irrigation, and as soon as you had a harvestable crop, you had to scoop them all up, and you had to completely destroy all the plant residue, removing all that alternative habitat. And then also there was a big emphasis on nitrogen management. So this is one that I don't find the evidence for completely compelling, but in general, the trend with hemipterans is if you have a lot of nitrogen in the plant, you're going to get a lot more hemipterans hanging out on it. This has not been definitively shown for whiteflies of all things, but there was still an advisory that you do not fertilize the plant after it has bloomed, being that you don't get a whole lot of benefit out of that since it's already bloomed. And it's also the time when the whitefly is going to be the most damaging and the most attracted to the plant. So you want to make that plant unattractive. Also, they didn't just modify the harvest dates for the melons, but they also shifted growing periods for cotton. So prior to the biotype showing up, the typical practice was that you would plant your cotton sort of like early summer, and you'd harvest it in October or December. Just kind of a nice long growing season. The challenge with this was that here we've got the average population of whiteflies over a month. So this is 2 different years, but you can see this general pattern that whitefly populations kind of peak in late summer, sort of July, August, September. Sort of the same thing here, July, August, September, we have very high populations. So essentially they were hitting their highest populations during the time where you had a whole lot of limb hanging out and the crop was most vulnerable to the damage they were going to sustain. So what growers ended up doing was they shifted their plantings earlier, so they were planting well ahead of when whiteflies would show up, and they would harvest them much earlier, say July or August, rather than in October or December. So essentially you put out the crop, as soon as you have bulls set, you defoliate them so there's nothing for the whiteflies to live on, and you harvest them as quickly as you can, just to avoid any sort of buildup of populations. And then finally, there was an effort to use host resistance. This is another one that's not completely convincing, because there's no true resistance to whitefly in cotton. We don't have real antibiosis or antizoonosis. Rather, we have it that whiteflies tend to prefer hairy plants, so pubescent leaves, to feed on and reproduce on, as compared to glabrous or hairless varieties. And so they really shifted towards planting these hairless varieties in Arizona. The thing, though, was that the vast majority of plantings were already hairless in the first place, so it was like a 4% shift in variety. So I don't think it had a huge impact on the number of whiteflies in the system. Where there was a lot of help, though, was in the Imperial Valley, where it's really dominated by alfalfa. They shifted to a whitefly variety, whitefly-resistant alfalfa variety. And so that really cut down on populations that were hanging out in this sort of reservoir-type crop. All right. So area-wide impact, the second section of this bottom base. So area-wide impact essentially is all those avoidance tactics that have to be applied across communities with multiple fields, multiple crops, and non-crop targets. So essentially it's what it sounds like. It's area-wide, like we've been kind of hammering on the last 2 sections. And so this mainly was concentrated in 2 major factors, which was crop placement. Essentially, people figured out that there are certain crops that are huge sources of whitefly. So spring melons, fall melons, vegetables. In Mexico, they were growing a lot of soybean, and that attracted whiteflies like crazy. So if you just don't plant near those, you're less likely to get whiteflies in your cotton. There was also a lot of effort placed in alternative host management. So essentially, once those melons are harvestable, get rid of them. If you have an abandoned melon field somewhere, just plow it all under. Get rid of any sort of thing that these whiteflies can live on. And a lot of this work, the crop placement and alternative host management, was really taken care of through these community programs. So generally, growers all organized together into these collectives, like we see in a lot of area-wide programs. And they did a lot of work sort of sharing their own monitoring data. They would chip in to share costs for taking care of these non-target areas, They would coordinate sprays with one another to maximize their output. And all of this just really made these approaches much more successful overall. And then finally, we have the last one, which was exploiting the pest ecology. And this is something that just really didn't take off in this system. They didn't have a whole lot of highly successful tactics against whitefly in terms of its ecology. The only real thing that they had that was successful was that they did a really good job of conserving the natural enemies by applying IGRs. So it turned out, when they started applying these IGRs early in the season, they would spray them, and they would see that the whitefly populations would be knocked down for anywhere between 6 to 8 weeks. And that really impressed the growers because the active period for the pesticide was about 30 days. So we're talking about 50% more control than you would expect to get from this pesticide. And as it worked out, it was all sort of residual effect from the fact that you would knock down the whitefly population, and then at those lower levels, the biocontrol would keep it under control for a while before they got back up to another outbreak. And so yeah, they were basically getting about 50% more control than they were expecting from this tactic, which was really nice. And so finally, it raises this question. We put a lot of effort into this IPM program. There were a lot of researchers, a lot of growers involved, and it really makes us wonder, did the IPM work? Was it the IPM that got rid of the whitefly problem, or was it just a fluke? Could this have been done some other way that didn't involve nearly as much work? And the reality is it's kind of hard to say whether it was the IPM or not. What can be definitively said is that after the IPM program was established, whitefly populations did decrease. So IPM was fully established in 1996, and after that point, the cost of sprays right here went down significantly. The chunk of the sprays that was due to whitefly especially reduced. Similarly, the total amount of insecticides applied reduced substantially. Again, the chunk due to whiteflies especially so. So clearly there was some good control of these whiteflies. The challenge is that there's a lot of confounding variables, and we don't have a lot of data to say what was the most effective part of this. Because no one did any surveys of growers to see how many of them were using these programs, and there were a lot of different control tactics being applied at the same time, sort of like an ideal IPM program would have. So, what you see a lot of, though, is if you talk to growers in the US, they very quickly point at the IGRs, the insect growth regulators, and they will usually credit that with the majority of the success of the program. They will say, if we didn't have those IGRs, we would have never taken care of the problem, and it would have, essentially, we would have had to have dealt with high losses for a long time until those IGRs came along. And this kind of makes sense, because they provided nice long-lasting control, they were selective, they maintained biocontrol in the field for a long time. However, if you look at the Mexican populations, it kind of confounds this a little bit. Because in Mexico, the IGRs were not approved until much later. It took them a longer time to move through the regulatory system there. And so they didn't have the IGRs. They also didn't have access to imidacloprid. And so their entire control program was focused on avoidance as opposed to chemical methods. And they found that just by reducing the amount of cotton they grew, reducing the cotton growth window, and removing a lot of the summer hosts and reservoirs, they got more or less identical reductions in whitefly populations. And so it seems that while IGRs definitely have an important role to play in this, you can't attribute all of the success to them. And maybe you can't even attribute the majority of the success to them. So, point being, IGRs did coincide with this huge reduction in insecticide sprays, going from 12.1 sprays per season down to 1.9 within about 4 years, so even less time. The other thing to keep in mind here is that a lot of those insecticide sprays may have been due to the fact that 2 really impressive chemical technologies came out in that period too. 1996 was the first time that BT cotton was grown in a lot of these regions. So we were knocking down a lot of pesticide sprays for LEPs. And also, it's when imidacloprid came out. And imidacloprid has proven very effective at controlling most all pest insects across the board. So, one real benefit, though, of these IGRs is that since they have been put into the rotation, and we've really focused on IGRs and non-pyrethroids, most all whitefly populations in Arizona and California have regained their susceptibility to pyrethroids. So essentially, we removed that pyrethroid selective pressure, and the populations went back. So we've regained a tool that was lost. And so that's really cool, that these rotations actually worked very well. So all in all, it looks like it's hard to say what part of the IPM program worked the best, what was the most essential, but what is clear is that these parts do work together to provide really nice control, and that this paradigm that was set up in 1996 is still going strong 20 years later. So what's nice about this is it's a big investment up front, but ideally these combinations of techniques are going to last for decades into the future. So with that, I guess that's the end of IPM. So,
No class Tuesday?
well, there's a review session. So that's the end of new material in IPM.